So I'll go. We're just about to noon, so I'll give a little bit of an introduction to Phil, and then we can get things started for the day. So very happy to have Professor Lubin here from UCSB. Recently had awards related to power beaming from both the LuSTR and the Watts on the Moon Challenge from STMD. Professor Lubin is very proficient, prolific in publishing more than 450 papers, and has received some Gruber Prizes in cosmology as well. So I'm very excited to hear his thoughts on power beaming as well. Yeah, so let's see, go ahead. And I think, Phil, if you're ready to share your screen, you can go ahead and get started.
Okay, yeah, looks like I need permission to start sharing, which I have. I'm going to bring this up. And okay, can you see the full screen?
Yep, it looks good and it's on the right side.
Great, okay. Yeah, so there's a lot of material here. I apologize for rushing through it, but I want to give you an overview of what we're doing in our various directed energy / power beaming programs. Please go to our website if you want to get more information. Almost everything is there, although the LuSTR stuff is not there yet, but our other material related to directed energy phased arrays, power beaming is there. So we've had 3 NASA NIAC phase 1 and 3 phase 2 awards so far. We have LuSTR, Watts on the Moon, some DoD support, a number of private foundation supports as well. There's a lot of material there. I draw attention to 2 recent papers that might be interesting to you, though not so specific to lunar work. There's a paper on using directed energy long-range beam power for ion engine propulsion for fast solar system missions. I think you might find interesting. That just came out in February. Again, all these are on our website. And then a very recent paper this month on long-range beam propagation using phased arrays, including atmospheric perturbations for Earth to space applications. A number of our funding agencies are here. NASA, the NIAC program, Emmett and Gladys W. Technology Fund, Breakthrough Initiatives, Limitless Space, and then one of our major collaborators is Lincoln Lab. Lots of papers here. I'm not going to bore you with it, but please check out our website. We have about 57 or 58 papers now on the directed energy portion of what we do. A lot of them related to futuristic opportunities that are really transformed by directed energy. These ultra long range beam power possibilities. So I urge you just take a quick look at it. You know, they're quite technical, but you might want to read through them and check it out. I would say it's no not an exaggeration to say that wireless power beaming precedes wires. So it's been done for in my work, which is mostly early universe studies, 13.82 billion years of wireless power beaming, and wires are, you know, maybe 200 years or so roughly. Early work, of course, you know, we had the excellent work of a number of people, including Tesla, a little bit misguided, but kind of in the right vein. So this is a great area which has become more recent with the advent of the Tesla Corporation, but certainly, you know, a very interesting individual that you might want to read about and see what he was trying to do. Lacked a bit of fundamental understanding of what we've now considered to be electromagnetic theory in terms of how he was applying it, but this is really near field power transfer rather than long range far field power transfer, which we're more interested in. Though there is some work on near field on the moon, if you look at some of the recent work there for very, very short range inductive coupling. So our program is actually not specific to the lunar applications. In fact, we have a roadmap to the future, which proceeds from laboratory testing to Earth to LEO GEO, long range lunar point to point, which is where we are with the LuSTR program, to solar system missions where we beam power, as was discussed a little bit yesterday by Bill. We have a joint program with JPL on this. And then eventually one can imagine, it's not so fantastical to think about fast human transits including a possible 30-day mission to Mars enabled by directed energy. And those of you who might have studied nuclear electric propulsion and the ideas for getting to Mars quickly will recognize this as essentially like nuclear electric propulsion without the nuclear reactor. So you save dramatically on the mass. Obviously, it's difficult to do. And then eventually outside the solar system, including the possibility for relativistic missions. So LuSTR we consider to be kind of on the ladder that we're looking at, relatively low on the ladder, sending power over roughly kilometer ranges with hundreds of watts to kilowatts of power. It's very, very doable. In fact, I can hold in my hand in our laboratory up to about a kilowatt of electrical to optical conversion. And I'll get into that in a bit. The left-hand side here, I'll show you lots of data. So again, refer to our website because you're not going to have a chance to absorb it all here. This is spot size in blue in meters. So here's 10 centimeters. Here's 1 meter versus target distance in kilometers. Here's 1 kilometer, which is the LuSTR example that we were asked to look at. This is for a single mode diffraction limited optical system. I have a couple of examples here: 1 centimeter diameter optics, 5, 10 centimeters, and then 1 meter optic. The upper one here is a 1 centimeter optic line. So this is something, much significantly smaller than your hand, which is of order 10 centimeters. And this is the spot size you'd achieve at 1 kilometer. You'd achieve about 30 centimeters diameter with a 1 centimeter optic. And the system we're building for the LuSTR program is 10 centimeters. So you'd actually achieve about a 1 centimeter spot at a kilometer if you run diffraction limited, and this is at 1064 nanometers. The power level does not make any difference for the spot size. On the right-hand side here, I show the spot flux. Just ignore that for the moment. So this is very doable with a very small power beaming system. In fact, the system that we have now is under 10 kilograms, including the laser and the pointing apparatus. So it's very ripe for a demonstration mission, which we're in the process of discussing with CLIP's provider. This is the basic idea. You have a high power laser. We're going to be running multi-mode for simplicity. We'll be operating around 1 micron. I'll discuss some of the details there. A variety of cameras to keep track of targeting. We can hit multiple targets. We'll have a communication system between the target, which in this case is shown as a rover, and the sort of we call it parent-child. Parent provides the nutrition to the child that's hungry, and the child just says, "I'm hungry, so feed me." So there's RF comm, there's laser comm, there's power redirection. We do not let the waste heat go to waste. We actually use it because a lot of the energy balance is in keeping things warm. So we have a warm box inside. We have actually a rather, I'd say, clever scheme to keep things warmed in the entire lunar night, which if you're interested, we have a scheme that can basically take any electronic system and keep it warm for of order a month using only its internal energy, including very, very small systems under a kilogram. So please reach out to me if you're interested in that. This is, we have a lot of students involved in our programs. I'll show you later. They love coming in the lab and burning holes through things and working with us. This is actually a high school student. We have had over 100 students. I'll show you at the end some pictures of that. This is a small rover that we have. It has a LiDAR system. It has adaptive machine learning. It has, kind of many of the things that you would want for a lunar rover. Cameras, as I said, LiDAR, and then keeps track of where it is and is completely autonomous. Longer range, what we would like to do, say within the next 5 years, perhaps a little longer, is place an asset on the lunar surface and then send a beacon lock back to the Earth so we can actually lock our system onto it. And I'll explain why this is of interest. So currently we're building, in addition to the LuSTR program, we're actually building a system to be able to transmit power from Earth to Moon at a low level just to show it can be done. This is how the moon got its spots. If you ever read that as a child, we can actually transmit from Earth to moon with 3 small systems, actually. They're only about 10 watts each, and we spread them out roughly 100 meters on the Earth. And then we'll produce a diffraction pattern on the moon, which you can take a movie of, and we can project movies on the moon. So if you want to watch a movie on the moon, which might violate some interplanetary copyright, I'm not sure, but it's possible. So solid state lasers are extremely efficient. This one's 300 watts in our lab. This one's up to about 400 to 500 watts. You get about a kilowatt of optical power per kilogram of mass. And actually, we can do even better than that. Currently, about 50% efficiency conversion of electrical power into optical power. This is a multi-mode system. We do a lot of work in our lab on single mode optical systems. We build almost everything in our lab. This is a commercial unit, this actually comes out of a tactical weapon system, but they're very compact and extremely efficient and getting even better. This was alluded to yesterday. One of the things we'd like to do on the moon is transmit over long distances. Not having an atmosphere is a wonderful advantage. So this is a tower-to-tower system. Lasers can be on the ground or on the tower. And here we have the laser on the ground. Optics going up to a transit mirror, transmits to the other side. You get about 120 kilometers for every kilometer of height of the tower. So if you want to build a 100-meter tower, you can get a border of not quite 40 kilometers of range. So this is a way of going, fairly long distances. And I'll show you a comparison between the mass of wires versus the mass of directed energy or power beaming systems. Obviously, at some level, the power beaming is more efficient in terms of mass than is wires. And clearly that's the case for the sun. We don't run an extension cord from the sun to the Earth. We use wireless. Short distances use wires, and long distances use power beaming. The trade-off space for the moon is probably around 10 kilometers or so, depending on the types of wires that you have. Ignore this, okay, but we do a lot of very technical work on how to optimize optical systems. This is spot size for single mode, where you have a single spatial mode, and this is for a multi-mode system over here. For LuSTR, we will use multi-mode systems. It's simpler and has less complexity in the system, and works just fine for the distances we're going to. For long range transfer, say Earth to moon, point to point on the moon over long distances, we would go to single mode systems. Okay, so this is a real system. Here's a CAD drawing of it. Here's the actual physical rendition that we put together last year. And then here's operation in the lab. This is a 4-pi beam director periscope design. So it rotates in azimuth and in elevation. You could use it for powering drones on the Earth, helicopters on Mars, a rover to PSR on the moon, for example. So this will form the basis for the LuSTR actual system that we'd like to deploy on the moon. This, by the way, is the spot on a photoconverter in the lab. And again, at about a kilometer, we would form a spot for this system because it's multi-mode. We would form a spot which is of order a few tens of centimeters at a kilometer for a 5-centimeter optic. The one we're building for LuSTR is 10 centimeters, so it'd be a few centimeters at a kilometer. Went to single mode, it'd be even smaller. This is what we call our tower of power. For those of you that may be familiar with the group out of Oakland, which is where I spend a lot of my time. Basically, you put one of these things on a high tower, and then you can hit any target within the horizon. And here the horizon is about 20 kilometers in radius. So you could be sending power to a rover, a person, a base, whatever. You could imagine having a nuclear reactor here or bringing in power from solar, depends on the application. So we're working both internally, where we have silicon at UCSB, as well as with Spectra Lab, who works on indium phosphide, indium gallium arsenide, um, a variety of compounds. So these are their predicted and achieved conversion efficiencies. So here's 60% here. So they've achieved a little over 60% at 800 nanometers, while at 1064, they've only achieved about, it's actually excellent, 45%, but they should be able to achieve about 55 or above at various levels of illumination. So just for reference, one sun is 0.1 watt per square centimeter. So this is 2, 6, and 20 suns. I'll show you real data in a moment. So this is good. It's not bad. It's going to, of course, get better. And it's another way to look towards the future for more efficient conversion devices. But already, they're very, very good. Okay, so this is something that we did in response to a request to compare the masses for cables versus the masses for wireless transfer. And directed energy can be more effective, mass effective than cables for long runs. So what we did here is look at various runs and various power levels as a function of voltage. So why do we do as a function of voltage? As you go to higher voltage for cables, the mass of the conductor goes down, but the mass of the insulator goes up. So there's actually a minimum in the mass. This is the mass for a specific run. So this is the conductor mass plus the insulator mass for aluminum wires. Copper wires about twice the mass. And obviously in a PSR where it's cold enough, you could run superconductors. So this case is for non-superconducting wires over long runs. And what we looked at was runs out to 100 kilometers. So there's different labels here. Don't worry so much about the specific numbers, but just note that there is a minimum for specific cable design as a function of voltage. So typical voltages for the minimums are around 1,000 volts. So that's problematic for some cases, and you have to design the insulator appropriately. We do a lot of testing in our lab. So here's testing at 888 nanometers, illuminating a cell here. Do a lot of this in our lab. So here we tested both the UCSB silicon cells and then indium gallium arsenide from Spectra Lab. Our efficiency actually is not bad. At 888, we achieve between 35 and almost 40% efficiency because we're close to the band gap. So that's terrific, actually. Very low cost and allows us to get rapidly started on the program. And then we'll be using more efficient cells from Boeing as well. Same thing, but at 1070, this is for an NRL program that we're working on. Again, we do a lot of cell testing in our lab. We illuminate with rather high power lasers. 1070, we've achieved about 28% efficiency using our silicon and about 45% with Spectra Lab. We should be able to do even better as they fine tune their process here, probably up to about 55%, but currently about 45%. Okay, and these are actual cell tests. Here we tested 24 cells. And these are large cells too. Here's an array photo. It looks like looks like something on your roof, but it's obviously designed for laser transfer. Okay. So long-term is very different. And I want to just spend a few minutes blasting through a bunch of slides here. Our long-term vision is not to go kilometers, it's to go megameters to AU. So here's kind of a artist's rendition of what we might want to do from the lunar surface, go surface to orbiter, surface to Mars, for example, Earth to Moon directly, tower to tower, rim to PSR. Here's Earth to Leo, Geo, going to Mars, etc. So this is part of a long-term vision that actually most of our work goes into this part. Obviously, LuSTR is very important to us that we just received funding for, but the work we've been doing over the last decade is focused on this long-term vision. There is a vision of going to Mars and the outer planets, as was discussed a little bit yesterday by Bill. You can go from the surface of the Earth because of Earth's transmission is actually quite good. And then very long term, it's the only way I know to achieve relativistic capability. And so that's using direct momentum transfer rather than ion engines, which do not work for relativistic flight, but direct momentum transfer does work. I'll not dwell on that for this talk. This is the transmission of the atmosphere. We run a site at 4-kilometer altitude up in the border between California and Nevada. And at 1.06 microns, the transmission is around 95% on a clear day. So it's excellent. It's actually better than millimeter wave transmission, which we do a lot of for our cosmology program. I think a lot of this has to be kept in context. People often say, oh, it's impossible to build something big. So I did a lot of work when I was a graduate student in particle physics and cosmic rays. And, you know, if you had told Ernest Lawrence, seen here in 1932 with his first cyclotron, that someday you'd be building a particle accelerator that's, you know, much larger than the whole San Francisco area, people would have laughed at you, but yet we're doing that. So in our case, we do not have an upper limit in power. So this was asked yesterday. There is no upper limit in power. There's an upper limit in flux when you start tearing apart the vacuum, but that's vastly higher than anything we'll be doing. Okay, so this is done by parallelization. You build a phased array and then combine the phases in free space. So there's no upper limit in power, no upper limit in aperture size. This is not what we are doing for the LuSTR program, but it's part of the long-term effort to, say, send power directly from Earth to Moon or from Earth to spacecraft. I'm just going to show you a couple slides of what we do in our lab. It looks like a gigantic mess, but it actually has a purpose. So this is a phased array in our lab, basically at power scale. So we do all our own photonics. We build our own devices. A lot of stuff's done in fibers, so you have to master a lot of photonics. This is about 43% efficient. This is single mode, which is actually pretty good. And the system works, which is really really nice. This is a phased array diffraction pattern using 8 elements. So hence you see a lot of side lobes here. But this is a beacon locked system, and the beacon works really well. I'll just blow through this. A lot of this is the mathematics of phase convergence, which I won't bore you with, but it's there's a lot of work that's required there. Here we show the same kind of system, but introducing perturbations in the system. This is a deformable mirror. So we introduce atmospheric perturbations to show that we can overcome them. So we can go Earth to space if necessary, although I'd prefer to go lunar surface to space if we could. Just another issue. I'll go through that. So here's a quick movie. I'll try to end very soon. Beacon on, it'll lock in a moment. There you can see it locked with the beacon, beacon off. It goes out of phase, beacon on, beacon off. So this technique actually is incredibly efficient at locking arrays. You can do custom beam formation. So here is using a helical phase across the system. So we're producing a donut beam. We can write NASA on the moon. We can actually literally project movies on the moon if necessary. Not really something practical, but the system is incredibly robust and flexible in beam formation. This is what we're building in our lab for a series of array tests to build out a full-size system. Each of the subarrays, sub-elements is about 100 millimeters, and this is for dealing with the atmospheric perturbation scale size. On the moon, you'd actually make these larger because you don't have an atmosphere to worry about. We've now achieved lambda over 100 at 11-kilometer radius, which means this is the equivalent of a 22-kilometer diameter array, which is an outrageous statement, frankly, that I didn't think we'd be able to do. We're down to about 5 nanometer RMS over enormous distances. So this works incredibly well. This is just a chart from this paper on fast solar system missions. This is looking at getting to Mars in a month, which is possible, at least looks like it's possible. But I draw your attention to the one here, and I'll try to finish up in just a minute here, of sending a CubeSat to fly by Mars in 120 days. This is not a lander, but flyby. It's a great way of attracting students. We've had more than 100 students in the last 5 years in our lab. They really love it, engages the public imagination. great way to increase diversity and get students involved in really high level, futuristic, as well as immediate applications. So conclusions, this works. It's a practical way to go. Small scale, directed energy, power beaming, very relevant for lunar, Mars, LEO to LEO, etc. Then you work your way on up this ladder that we talk about, this technological roadmap to high-speed spacecraft, molecular composition analysis, which had a program on planetary defense, long-range LiDAR, and it has a really robust future to it. So I'll stop there and just make one note. This requires a long-term dedicated program if you want to bring it to its transformational conclusion. That's the hard part. Right, thanks.
Thank you so much. I really do. You said that you would be able to provide these slides afterwards. There's a ton of information, so I really do want to get that onto our site for everybody to dig through all of this stuff and start trying to put all the pieces.
Condense it down. It's too big right now. I'll condense it.
Of course. Okay, so if you have questions for Professor Lubin, we're a little bit late, and I know you have a kind of a hard deadline coming up soon, but maybe we can take a question or two.
Yeah, I'm actually okay. I told people I'd be late, so.
Okay, great. So go ahead. You can post your questions in the chat. Maybe I can kick it off with a question. So you talk a lot about conversion efficiency throughout. Have you considered conversion efficiency when you're operating in a PSR down at 40 Kelvin and the band gaps get sharper and so on?
Yes. So there's nothing that kills the system at low temperatures. In particular, what I alluded to in terms of keeping things warm over long periods of time is another program. It'll be incorporated into the LuSTR program, but it's actually another program that allows arbitrary systems to survive over long periods of time. In terms of the photoconverters, which would run essentially at the ambient temperature, they actually self-heat when you start to illuminate them. So even though that's true, the band gap does change as a function of temperature. Sometimes it works to your advantage. You can actually get more efficient conversion, but sometimes it also pulls you outside. But when it pulls you outside of the band gap that you want, it will self-heat based on the power that you're dumping onto it and then pull it back. So it's self-correcting in that sense. We've run cells down at liquid nitrogen temperatures and brought them back up to operating just by self-heating. So it doesn't appear to be a fundamental problem. I think it's more of a thermal stress problem. You'd have to be careful how you mount things so they don't crack. But we have a lot of experience in cryogenics engineering from our cosmology program, so we're pretty used to matching CTEs and working on flexible systems.
Yeah. And so, yeah, I mean, I would generally think that things would kind of get better, but makes perfect sense that if you're not dumping it into the cell as power extracted, then you're going to get heat out of it and it will self-correct.
Yeah, and one thing to keep in mind is that because heat is often a valuable commodity in addition to electricity, as was discussed yesterday, that we do not want to just dump the heat that comes in. We will try to store it in a thermal battery versus an electrical battery on board. So it's the conversion efficiency, while it is of order 50% on conversion from photons to electrical power, the other 50% is extremely valuable and could be stored, in a thermal battery, a phase change battery, for example.
Yeah. Here's a question from Kieran. How close to diffraction limited spot size can you achieve for single mode systems?
Yeah, so this gets into this question of what we would call STREL. So, how close to theoretical can you get? By the time you get to surface roughness, surface figures, which are of order lambda over 10, so a tenth of a wave, then you've achieved STRELs, which are typically of order, say 80% or so theoretical. We've shown that we can achieve in our large aperture systems better than lambda over 100. So that's essentially like the Hubble Space Telescope had it been ground correctly. The case for the small systems like LuSTR, we will be running multi-mode, so it's less of an issue because we're not trying to run in diffraction limited mode. If we ran LuSTR in diffraction limited mode, because the optics are relatively small, like roughly 10 centimeters, it's very easy to get an optical system, whether it's refractive, diffractive, or reflective, which is very close to diffraction limited. And we have systems already in the lab that are at scale for LuSTR, where we get strels above 80%. So, 80% of theoretical efficiency.
Yeah.
You do get a little bit of side lobe, but it
Mhm.
typically is significantly less than 10%.
Okay. There's a couple interesting questions coming in that are sort of extending what power beaming could be used for and what its needs to take in mind. So here's a question: could a crater rim source be used to gather LIBS data from selected points on a polar crater floor?
Yeah, so excellent question. So there's two fundamental ways of imagining doing remote analysis, where you don't send a physical thing, but you basically use the photons to either excite or thermally ablate material and then analyze it remotely, much like the LIBS system on Mars. So yes, one of the programs that we had uses laser ablation and then looks at the molecular composition through spectroscopy of the ablated material. What LIBS does is ionizes the material, and instead of looking at molecular composition, looks at atomic composition. So that's a high power pulse. You ionize and then you look at the spectroscopy of the ionized material. So the answer is yes. And I didn't dwell on that, but that's a part of another program we have, which is doing long range remote analysis. And indeed, you could think of things like, well, I'd like to melt a patch that might have water in it at long distances, and you don't need high flux to do that. You can melt it and then look at it with a high resolution optical camera. You can look at it spectroscopically. And so there's all kinds of things that you could do in terms of remote sensing, including mapping out the crater in a laser scanning operation, where you actually do detailed topographical analysis, which then would set up sort of like a GPS-like grid, but using a LiDAR system for doing so. So there's all kinds of things that are additional to the power beaming portion, where lasers would play a role. And we take a very much synergistic attitude towards this. As I spoke about yesterday, if someone says I need 100 kilowatts at 100 meters, I'd say, great, use a cable. But if you want to hit a rover that's mobile, or 100 rovers, then you might want to consider power beaming. It's not an either or. It's a mission specific application question.
Absolutely. Just maybe one more question, and then we'll get to the other speakers. I did build in some time into the agenda, so we have a little bit of extra time to let these conversations go.
Thank you.
But there's a question from Dan Hawk. Are there advantages to shorter duty cycles, or are you generally operating at full duty?
Generally, we operate CW. So this is a good question. The question I'll restate it is there advantage to running short pulses versus just continuous operation? For some applications, such as LIBS, you have to run short, high power, short duty cycle pulses. For us, there's no significant advantage in terms of the power beaming portion for running pulsed, and in general, there's a disadvantage to doing so, as it's less efficient. So we run CW. There are applications where you want to heat something up, or ionize something, or ablate something, where you want very high peak powers for short periods of time. Fundamentally, the system design doesn't change. It does change the photonic side of how we would achieve high peak powers, but for the LuSTR application, we're running CW.
Okay, great. Well, thank you very much. There's quite a few more questions in the chat. If you have a minute still, you could respond to them in the chat, or we can take this conversation also up on Confluence and in the following telecons we'll have.
Yeah, people can email me as well.
Okay, great.
Thanks a lot.
Yep, thank you very much.